In the previous videos, we explored the hydraulic calculations for fire sprinkler systems. In this video, we introduce the free online tools developed by NSVSOFT, designed to streamline and simplify those calculations. With these tools, designed for educational purposes, we can perform hydraulic calculations for tree piping configurations with uniformly spaced sprinklers. They allow us to determine the equivalent K factor for parts of the system, calculate the equivalent length of fittings and valves, apply correction factors based on the C factor and internal pipe diameter, and evaluate the safety margin using flow test data versus system demand. In addition, the tools include practical features for estimating pressure loss in pipes and identifying the optimal K factor for sprinklers. In all sections of these tools, values should be entered in the green cells, selections made from the blue cells, and the results will automatically appear in the white cells. Let's see how to perform a hydraulic calculation and apply these tools through an example. Imagine we are designing a wet pipe fire sprinkler system for a textile manufacturing occupancy. The building dimensions are 80 by 48 feet, with a ceiling height of 10 feet. According to Section A4332 of NFPA 13, this occupancy is classified as Ordinary Hazard Group 2. Therefore, based on Table 102421B, the maximum coverage area for standard spray sprinklers is 130 square feet, with a maximum spacing of 15 feet. Table 192311 specifies that the required density for Ordinary Hazard Group 2 is 0.2 gallons per minute per square foot, with a design area of 1,500 square feet. Since we've already published videos covering most of the topics related to designing the sprinkler system in this example, we won't revisit those details here. Instead, we'll display the titles of the relevant videos in the top right corner of the screen. For educational purposes, we will apply standard spray sprinklers with a K factor of 5.6 and standard response sensitivity. For above-ground piping, we will use black steel Schedule 40, and for underground piping, cement-lined ductile iron class 52. Let's assume the fire sprinkler system is supplied by the municipal water network. The flow test indicates a static pressure of 100 psi, and at 700 gallons per minute, the residual pressure is 80 psi. We begin designing the sprinkler system by locating the sprinklers. In this example, we select a tree piping configuration. The sprinklers and branch lines are assumed to be at the same elevation, connected to the cross main through a 1-foot riser nipple. Based on the sprinkler layout, the spacing between sprinklers is 12 feet, and the spacing between branch lines is 10 feet. Therefore, the coverage area of each sprinkler is 120 square feet. The design area includes 13 sprinklers as shown in the figure. At this stage, we estimate the pipe sizes. As explained in the step-by-step video, the initial pipe size selection is arbitrary. We may choose sizes based on the pipe schedule method or any other order. Using these assumed sizes, we calculate the system demand. If the water supply can support the demand, the initial pipe sizes are acceptable. However, if the supply cannot support the demand, or if we want to reduce system cost, the pipe sizes must be adjusted. In this example, let's assume 1-inch pipes feed a single sprinkler, 1 1/4-inch pipes feed 2 sprinklers, 1 1/2-inch pipes feed up to 4 sprinklers, and 2 1/2-inch pipes are used for the cross main and riser. For the underground pipe connecting the sprinkler system to the municipal water network, the pipe size is 4 inches. As shown in the 3D view of our system, the sprinklers are installed directly on the branch lines, which are connected to the cross main through a 1-foot riser nipple. On the riser, we have a flow switch, a wet alarm valve, and a butterfly valve. In addition, a backflow preventer is installed on the 4-inch underground pipe. Now we need to define nodes for the hydraulic calculations. As explained in the step-by-step video, nodes should be placed wherever the flow rate, C-factor, or pipe size changes. In addition, nodes can be added to make review and analysis easier. In our example, beyond the mandatory nodes required for the calculation, we also define a TOR node at the top of the riser. The BOR node is located where the pipe type changes from black steel Schedule 40 to cement-lined ductile iron class 52. The final node is the test point, where the flow and pressure are determined from the flow test. Before entering data into the table, let's establish some assumptions about node elevations. In this example, we set the floor elevation as our reference plane. Since the building ceiling height is 10 feet and the sprinklers are installed 1 foot below the ceiling, the elevation of nodes 101 to 113 will be 9 feet. As the sprinklers are installed directly on the branch line and the cross main is connected to the branch line through a 1-foot riser nipple, the elevation of the nodes on the cross main will be 8 feet. We also assume that the elevation of the BOR node is 1 foot above the floor level. Finally, because the flow test is performed through the outlet of a fire hydrant without digging into the ground, we assume the test node is 2 feet above grade. Now we are ready to begin the hydraulic calculation of our fire sprinkler system. In the Hydraulic Calculation tab, we enter the project data. Since this table is similar to the detailed worksheet in NFPA 13, we recommend watching the video we published about it to become familiar with the cells in this table. By checking the box, the software will automatically update the pipe type and size in the following sections. This option is useful for saving time when entering the initial project data. However, for optimization, it is better to leave the box unchecked. Before filling in the table, we need to enter the sprinkler coverage area and the required density. In our project, the coverage area of each sprinkler is 120 square feet, and the required density is 0.2 gallons per minute per square foot. By entering the data, the software determines the required flow rate and records the calculation in the dedicated cell. Now we can begin entering the data for the first section of our fire sprinkler system, located between nodes 101 and 102. The elevation of these nodes is 9 feet. After entering the elevations, the software calculates the pressure change. Since both nodes are at the same elevation, the pressure difference will be 0. We assumed a K factor of 5.6 for the sprinklers. By entering this value, the software calculates the required pressure at sprinkler 101 based on the flow rate and K factor and records the result in the dedicated cells. Now we select the pipe type. The built-in pipe library includes internal diameters for Schedule 10, 30, and 40 black steel pipes, copper types M, L, and K CPVC pipes, and cement-lined ductile iron class 52. In our example, the above-ground pipes are Schedule 40. Since we checked the box to sync changes to subsequent entries, the pipe type in the following sections of the table will be filled automatically. By selecting the pipe size, the software records the corresponding internal diameter in the dedicated cell. There are no fittings to consider in this calculation, so we will leave those cells blank. The pipe length in the first section is 12 feet. Based on these values, the software calculates the pressure loss using the Hazen-Williams formula, along with the total minor and major losses, and displays the results in the dedicated cells. Regarding the C-factor cell in the software, since we selected black steel pipe, the C-factor can be either 120 or 100, depending on the system type. For dry pipe and pre-action systems, the value also depends on whether air, nitrogen, vacuum pressure, or vapor corrosion inhibition is used. The default value in the software is 120, but it can be changed to 100. If copper, CPVC, or cement-lined ductile iron pipe is selected, the software automatically assigns the required value without a selection option. In the second section, which lies between nodes 102 and 103, the pipe size changes to 1¼ inches. The other parameters remain the same as in section 1. Section 3 is similar to the previous sections, except the pipe size changes to 1½ inches. In section 4, we need to consider some important points. This section lies between nodes 104 and 1. The elevation of node 1 is 8 feet, as it is located on the cross main and 1 foot below node 104. The total pipe length is 6 feet, calculated as the sum of a 5-foot horizontal run and a 1-foot vertical run. In addition, this section includes 1 elbow and 1 T, both sized at 1½ inches. Let's enter these values in the table. When we input 8 feet as the elevation of node 1, the software calculates the pressure change due to elevation. In the equivalent length tab, since the default values for the pipe type and C factor match our example, there is no need to change them. According to the table, the equivalent length of a 90-degree standard elbow is 4 feet, and the T is 8 feet. We enter these values in the table and finally input the total pipe length in this section as 6 feet. In section 5, since there is no sprinkler and the flow rate remains the same both upstream and downstream of the starting node, we leave the K factor cell blank. The pipe size in this section is 2½ inches and the length is 10 feet. In section 6, which lies between nodes 2 and 3, we need to calculate the flow rate of sprinklers 105 to 108. As explained in the previous videos, we can apply the equivalent K-factor method for this calculation. Since the second and third branch lines are identical to the first branch line, we can use the equivalent K-factor of the first branch line to determine the flow rate of the similar branch lines. There are 2 methods for calculating the equivalent K-factor of the first branch line. The first method is to enter the flow rate and pressure at node 1 in the HC Tools tab, where the software then calculates the equivalent K-factor. The second method is to hover the cursor over node 1 and the software will display the value. In general, by hovering the cursor over the nodes in the Hydraulic Calculation tab, the software calculates the equivalent K-factor for the section downstream of that node. We enter the equivalent K-factor and the pipe length. In section 7, we follow the same procedure as in section 6. The K-factor is 18.5 since this branch line is identical to the previous ones. In section 8, which lies between nodes 4 and TOR, we need to consider the flow rate of sprinkler 113. Since this sprinkler is installed on the 4th branch line, and that branch line has only 1 sprinkler in the design area, we can't use the equivalent K-factor from the previous branch lines, which each have 4 sprinklers in the design area. As explained in the K-factor video, there are several solutions to calculate the flow rate of sprinkler 113. In this example, we use the equivalent K-factor method through the tab of the same name in the software. In the table, we enter the data for the branch line located in the design area. In our example, this section lies between nodes 113 and 4. After the data is entered, the software calculates the equivalent K-factor for this section, and we then input the calculated value into the Hydraulic Calculation tab. At the end of this section, there is 1 2½ elbow. From the equivalent length table, by clicking on the cell for this fitting, the software copies the value, which we can then paste into the dedicated cell in the Hydraulic Calculation tab. The pipe length in this section is 44 feet. In section 9, between the TOR and BOR nodes, we have a flow switch, an alarm check valve, and a butterfly valve. We take the equivalent length of the flow switch and butterfly valve through the equivalent length tab, and for the wet alarm check valve we use the manufacturer's datasheet, which specifies an equivalent length of 8 feet. The elevation difference between the start and end nodes of this section is 7 feet. We assume that 6 feet of this value corresponds to the pipe length, and the remaining 1 feet accounts for the devices on the riser, which are included in their equivalent lengths. The last section of our system is located between the BOR and test nodes. It should be noted that in the software, the final node must be labeled as test. This allows the software to recognize that the hydraulic calculation is complete and to calculate the system demand once the user has filled in the required cells. The elevation of the test node is 2 feet. This means there is a pressure gain due to the elevation change between the start and end nodes, and the software represents this gain with a negative sign. The pipe type is cement-lined ductile iron, class 52. By selecting this option, the software updates the C factor to 140. The pipe size in this section is 4 inches. In the final section of our system, there's a set of backflow preventers. According to the device's datasheet, the equivalent length is specified as 80 feet. As explained in the flow rate and pressure video, in most cases the values in datasheets are based on Schedule 40 pipe with a C factor of 120. Since in our system the backflow preventer is installed on a different pipe type with a different C factor, we need to adjust the equivalent length accordingly. In the software, the adjusted equivalent length can be determined in 2 ways. First, in the Multiplier tab, we find the correction factors based on our project. By multiplying these factors by 80, we can calculate the final equivalent length. The second method is through the HC Tools tab. By entering 80 and selecting the pipe type and size, the software automatically calculates the adjusted equivalent length. In this section of the system, we have a long-turn elbow. From the Equivalent Length tab, by selecting the cement-lined ductile iron pipe, the table values are updated based on the different internal diameter and the C factor. We can then obtain the adjusted value for the required fitting. We enter the equivalent length of the backflow preventer and the elbow in the dedicated cells. We also assume that the total pipe length, including both vertical and horizontal runs, is 40 feet. After entering the data for the last section, the software displays the system demand. Now we can check whether the water supply is able to meet this demand. In the Water Supply tab, we enter the flow test data. Since we do not have an inside hose connection fed by our sprinkler system, we add 250 gallons per minute as required by Table 19.2.312. Hose stream allowance is one of the least explained topics in fire sprinkler design, and we will cover it in a separate video. There are 2 ways to verify whether the water supply meets the sprinkler system demand: graphically or mathematically. In the graphical method, we plot both the water supply curve and the system demand curve on the log 1.85 graph. If the system demand curve lies below the water supply curve, we can conclude that the water supply is capable of meeting the system requirement. In our example, the static pressure of the water supply, meaning the pressure under no flow conditions, is 100 psi. At 700 gallons per minute, the residual pressure is 80 psi. The line connecting these 2 points represents the water supply curve. The first point of the system demand curve is located at 0 flow. According to the Sprinkler Hydraulics book by Harold Wass, revised by Russell Fleming, the pressure at this point is equal to the elevation pressure, also known as the static head, of the sprinkler system relative to the water supply. Since all sprinklers in our system are 9 feet above the reference plane and the test elevation is 2 feet, the elevation difference is 7 feet. Therefore, the elevation pressure is calculated by multiplying 7 by 0.433. The second point represents the flow and pressure of the sprinkler system. For the third point, we add 250 gallons per minute for the hose stream allowance to the system demand at the same pressure required by the sprinkler system. As shown in this graph, the system demand curve lies below the water supply curve, which means the water supply can support our system. The graph also indicates that the pressure available from the water supply at the system flow is 85 psi. In the mathematical method, we determine the pressure that the water supply can provide at the system's required flow rate using the formula shown here. This formula is noted in the third edition of the layout book published by the NFSA. In our example, the residual pressure of the water supply is 80 and the static pressure is 100 psi. We calculated the total system flow demand to be 599.6 gallons per minute, while the flow at the residual pressure is 700 gallons per minute. By substituting these values into the formula, we find that the available pressure is 85 pounds per square inch. The software calculates the available pressure using the mathematical method, and it also determines the safety margin in both psi and percentage. To calculate the safety margin in psi, we subtract the system demand pressure from the available pressure. To find the safety margin as a percentage, we divide the safety margin in psi by the required pressure and then multiply by 100. As we've seen in this video, although the system demand is lower than the available flow and pressure, providing a good safety margin acceptable to most AHJs, professional designers continue their work because they understand that reducing the cost of the fire sprinkler system is one of the key goals of hydraulic calculations. In the next video, we'll explore how to optimize the system and further reduce costs.